Dr. Sela will introduce. Our next speaker is Kuindersma, who is currently a senior director in robotics research and Boston Dynamics, leading the project of Atlas. He was previously an assistant professor in Harvard in the engineering computer science department. He finished his PhD in UMass and also his postdoctoral training at MIT with Ross Tedrick. Today his talk is about let's all just be friends. Model-based control helps learning and vice versa. Let's get started.
All right, thank you very much. You don't have to clap before. Gonna sort that out. This is a picture I took in Iceland. Hope you enjoy it. Okay. All right.
You are not able to see it on here, right?
That's okay. Just one slide telling you a little bit about who we are. So we are a commercial robotics company. Last I checked, we have something over 600 employees. We have 2 robot products, Spot and Stretch. Spot is a mobile robot platform that is deployed all over the world. I think every single continent except Antarctica. We're working on that. And there's a variety of ways that people use Spot. So there's people who are kind of researchy innovation groups that are doing things with it, either the robot itself or various sensor payloads and arms and things like that. And people are, one of the biggest footholds for Spot has been in industrial inspection. So getting a robot like this to just repeatedly walk around environments that have a variety of challenging features like staircases and irregular terrain, build maps, be able to go inspect things, read gauges, detect when things change, and so on, is actually pretty valuable. And so I'd say the bulk of how people are using Spot is in that space right now. Stretch is our warehouse automation machine, which is mostly focused on trailer and shipping container unloading of boxes. So the robot's deployed with a bunch of customers right now, and it has a lot of cool technology built into it. So there's a machine vision-based 3D box detection system that can be fine-tuned in the field. It's got a lot of smart gripper technology for grabbing boxes of various cardboard quality, which is a thing you have to pay surprisingly a lot of attention to. Grabbing multiple boxes at once and dropping them in a singulated way, being able to recover when it drops boxes, because inevitably it will drop boxes. And right now it's seeing something around like 500 cases per hour on average in various deployment settings. Lots of cool stuff there. Unfortunately, I don't have time to talk about that today. And then Atlas, which is our R&D platform, and I will talk a bit about Atlas today. So the work that we've been doing on Atlas over the past few years, I could just summarize is with the high-level goal of trying to make dynamic behavior easier to create. So we had at the time a very impressive, we thought, a robot that could, in principle, do many things, but in practice, it was very hard to get it to do any particular new behavior. And we wanted to be able to make things like jumping and flipping and running as easy to specify as moving an end effector around in space, right? And so that's been sort of how we've focused our work, and we've been exploring different design choices in the space in order to achieve things like this. And we occasionally will do kind of integration tests like this just to evaluate our progress in time and share things back with the world. Obviously, these things are very highly practical and of significant commercial interest. Most people who own factories want robots running around their factories doing things like this. So the way we think about this problem, I can kind of cartoon out this way. Basically, we wanted to be able to design behaviors using sources of data that we thought were easy to generate. Okay, so this could be things like trajectories, and maybe these trajectories come out of trajectory optimization offline. Maybe they come out of animations or human motion capture or teleoperation, whatever. And then we're going to take these trajectories and optionally we'll do something to them. We'll process them. Maybe we'll do a retargeting step onto the robot. Maybe we'll use them as input to some policy training process here, or maybe we'll learn some other type of predictive model that is used by a feedback control system that runs online at a high rate that is responsible for executing those behaviors and making appropriate adjustments so that the robot succeeds. And importantly, this feedback control system, we wanted it to be something that was pretty general. So it's something that covered the whole space of the robot's behaviors. And it was conditional. We could condition it. So we could say, I want to take you to do a particular behavior, and I'm going to tell you what the task is, what the goal is on the fly, and have the feedback control system be able to respond in a reasonable way. So that you're not just purely executing a list of behaviors that you happen to have thought of ahead of time. But the way that we marched through this over time was, first of all, step one is being able to do things like this at all, because we couldn't, or we could, but it would take years or months of engineers doing open-ended creative development in order to achieve something like that. We wanted to make that more of a repeatable process. Once we're able to do that, then we wanted to be able to improve generalization, so make the feedback control system able to be conditioned on goals. And the idea is that maybe I can take a small set of data and generalize that online in useful ways, or maybe this generalization process allows me to get away with lower quality data upstream. And then once we're able to do this, I think there's something interesting that happens, in that you now maybe made more interesting types of data easier to create. So now I can maybe get actual traces of embodied dynamic motion on the machines that I care about and feed that back into this process. And now that may allow me to make different decisions about how I'm doing offline compilation, or maybe how I'm doing feedback control in the future in order to make the robot better. So I'll talk a little bit about our progress and where we're at, kind of getting towards step 3. Okay, so step 1 is being able to do this at all. We made a design choice that we're going to focus on model predictive control. It's a class of control techniques that have been studied for many, many years in the control and robotics community, and see how far we could push it. So the choice that we made originally, and this is now a few years ago, was to leverage a representation that was pretty popular in the robotics community based on centroidal dynamics and kinematics. So here's a few of the papers that inspired us, but there's a long list of people who've published in this area. And so when you write down a model predictive controller, just so people are a little bit grounded too, just in case you don't think about these things, model predictive controllers are controllers that are optimizing for some trajectory into the future, say a second or two into the future. And the goal of the optimization is to choose actions that not only improve the state of the system right now, or the state of the system at the very next time step, but that improve the entire state evolution over that horizon. And so when you do that, you have to make some representational decisions about how to implement that optimization, how to represent the dynamic model, how to put costs and constraints together, and so on. And so this was an early choice we made. And what we did was we separated this problem into 2 cascaded MPCs. The first one just worried about the dynamic stuff. So thinking about the robot as a very simple, say, single rigid body with a variable inertial ellipsoid. And so this is optimizing over things like external wrenches, center mass, momentum, angular excursion, stuff like that. And then separately, we'd optimize a kinematic trajectory that was consistent with the momentum trajectory while also satisfying some other kinematic goals, like tracking a reference motion or something like that. So this is good in that these are like separately smaller problems and pretty easy to optimize, but bad because they're not connected intimately. So you maybe might not know about things like leg length limits when you're planning to put your forces on the ground, and that could be bad. So this can create problems. And what it means essentially is that this reference trajectory has to be pretty good. So when you do that, though, you can do pretty fun stuff. So here's just a couple examples. You've all seen things like this before. So here's a couple examples of an offline trajectory optimization to do front flips and back flips. And then you could take that reference motion and then input it to the MPC controller. And then voila, the robot can do those behaviors too. And as you can see, the matching between the reference trajectory and the robot is pretty close. And that's sort of characteristic of how this type of MPC we found. Doesn't have to be dynamic trajectory optimization that generates this data. You can use other sources too. So you can use motion capture, which we've done, and we've leveraged animation quite a bit too. So all the stuff we did with robot dancing was based on an animator who's doing purely kinematic animations of Atlas and Maya by watching people dance in YouTube videos. And we take the output of that, which isn't physical, but it's not terrible either. And we run it into the robot, and then you can do sort of extended long dance sequences. And this is, again, exactly the same MPC controller, no change in code, no change in cost or anything. So all the parkour behaviors, all the dance behaviors, all just using exactly the same controller. The only thing that's changing is the inputs going into it. And once we sort of got a hold on this whole system, we could start doing things like this pretty quickly. So going from a video of a person doing a dance move like this is actually, I think, from a BTS video. Fans of BTS might recognize that. I don't know. So going from that to a rendering on Atlas to running it on the robot is usually 0 to 1 iterations. It takes something on the order of a day. So this kind of thing just sort of works pretty well right now. But this is all just tracking reference trajectory. So you give me a list of things to do, and you want the robot to do it. Here's one process for doing that. What what we want to do is not just anticipate all the detailed motions we want the robot to do over time and then be able to select from in that list, or maybe doing light retargeting on the fly. We want to try to make these things a little bit more generalizable so that we can take the same set of data and stretch it to online behaviors that cover more and more cases. And so one really straightforward way to do that is just to look at the limitations, the simplifications we imposed on MPC in the first place and start to remove them. And so that's what we did. So the first obvious one was not to separate these two into two smaller optimization problems, but to combine everything together. So we're thinking about the kinematics and dynamics together and doing this online. So this sounds good and sounds pretty obvious, but it's actually a lot of engineering work to pull this off. So this is now a much bigger optimization problem, something on the order of 20,000 costs and constraints. And quite nonlinear. And so there's a lot of work that's baked in here, optimizing solvers and thinking carefully about how you're setting up problems and taking advantage of sparsity and all that stuff in order to actually make this work. But the thought was that if you put in this work, then you get some benefits like better robustness, more ability to innovate on the fly, do recoveries, things like that. And maybe we can start to take advantage of data that's less good upstream. So it doesn't have to be a really good reference trajectory. Maybe it can be a slightly crappier one that's coming from an unprocessed mocap, or maybe it's not even a complete robot trajectory. We're allowing MPC to sort of resolve the whole body motion from, say, task space motion objectives. So I'll show just a couple examples of how things got better when we made that change. Here's a different type of flipping motion where it's kind of rotating over multiple axes at the same time. And this is, again, something that an animator just created in Maya, so an unphysical reference trajectory. And running this on the robot required MPC to do a lot of innovation. And so in order to do that appropriately, because the reference trajectory was aphysical, the robot had to think about how to apply appropriate forces to actually achieve the required angular momentum around multiple axes in order to eventually get its feet on the ground, all while thinking about actuator limitations during push-off. So the timing and direction and magnitude of all those forces really matter. Once it's in the air, it's going to have to tuck in a way that's different than the reference motion in order to make its inertia small enough so that the rotation actually gets it to where it wants it to go. And if it's going to tuck its whole body together, it needs to know about intercollisions of all of its links. So it needs to pull its inertia in a way that doesn't infeasibly intersect the limbs together. So you can actually dump or a subset of the collision geometries into MPC and allow all this all these trade-offs to happen within the controller, and then you can get kind of neat stuff like this. And this is, and we found we went back to the old representation of the controller as a baseline, and we were completely unable to get this to work even in simulation. Here's just another example of just doing generalization. So this is the video I showed earlier of the robot doing a backflip off of a 30-centimeter box. So little secret, jumping off of boxes is way easier than jumping on flat ground because you have a bigger height gap. So you don't have to have as much angular momentum at push off. You can rotate slower, you can tuck less, and so on. So this was a reference trajectory designed for a 30-centimeter box. You put it on a 30-centimeter box, it jumps off. Great. You can take that same unmodified reference trajectory and now just tell MPC on the fly that you have to land on flat ground. And it's going to make all the appropriate adjustments in order to make that happen. So now, again, pushing harder in order to get more angular momentum. Inevitably, it takes off with not enough angular momentum. So now it has to tuck more in order to rotate around. It knows it has to get its feet on the ground if it has any chance of standing up a second into the future. It's still under rotate, so it has to land in a pretty awkward posture that's very different than the reference motion. It has to think about how to get from that posture to standing without colliding with itself or with the ground. And all of these sort of considerations just get sort of handled inside of MPC. Here's just another fun one. So if any of you have worked on legged robot balance before and thought about step recovery, you've probably thought about things like capture points and maybe polygonal constraints that you've heuristically put on the ground that capture things like reachability and like avoiding legs colliding with one another. It turns out you don't really need any of that stuff anymore if you have enough of the model inside of MPC. So here what's happening is the robot's being pushed. When it gets pushed, we send a pretty dumb reference trajectory to the robot that says stand like a statue, but also march in place. And that's all it gets. And so all of the innovation about stepping in a particular direction, stepping ways that avoids collisions with one leg and the other, throwing the arms around in ways that avoids colliding with the body, tilting the body, windmilling the arms, all this stuff is just coming out of MPC purely. So this is all mobility stuff. And it's cool to start to see interesting dynamic mobility and some ability to generalize beyond the reference trajectories that you provide. But ultimately, you want to put these robots to work and make them affect their environment in useful ways. And so the way that we started to think about that was to take a kind of atlas angle to manipulation, where we're trying to manipulate large, inertially significant objects and take advantage of the robot's ability to apply large forces to the environment, and then figure out ways that the robot could not only compensate for those loads, but maybe even exploit them in certain situations. And so that was the impetus of our starting to do manipulation and putting together kind of fun little videos like this. But the way that we actually implemented that was, again, just to go back to MPC and just stuff more stuff into it. So now we're not just thinking about the robot whole body dynamics, but now we're taking object models and representing their states and dynamics and the constraints that exist between the robot and the object in terms of motion constraints, wrenches, intermechanism wrenches, things like this. And so now the robot can run MPC, and MPC is not just predicting the motion of the robot, it's predicting the motion of the robot plus the object. So I can put objectives on what I want the object to do, and then the robot will move its body in order to achieve those objectives on the robot, like putting the plank across the two boxes to build a bridge. And the way that we actually program that is, I think, kind of interesting. So it's not enough just to throw all these, constraints into MPC and hope that everything's going to be better. You actually have to think about the software architecture that lives above and how you're best going to exploit this capability in MPC. And so we have a way to kind of layer together different sources of motion goals and produce references to MPC that can be internally inconsistent. So I can tell it to do something with its body and its hands, or do something with the object and its body, or any combination of those things, and then ask MPC to kind of resolve potentially inconsistent input. So as an example, if you look at this tool bag toss that happens in this video, this is a cloth DeWalt tool bag that's stuffed with a bunch of wrenches. It weighs something around 15 pounds. And the robot's trying to throw this tool bag up to Brian, who's on top of the scaffolding there. So the way that we told the robot to do this was by giving a couple different inconsistent references to MPC. The first was do a 180. And this is a 180 trajectory that we had from like 2 years prior that we used for some parkour work. And then we had a representation of the tool bag, which is this kind of janky cylinder here, which has roughly the correct mass and inertia. And then we say, okay, you're going to have your hands attached to this relative location of the tool bag, i.e. cylinder, for this segment of the trajectory. And the goal is to get this tool bag up over there after and through some ballistic phase. So the robot has to think about a few things simultaneously. It has to imagine that it's grabbed the bag, and it needs to accelerate the bag such that it hits a boundary condition that will eventually, in a ballistic phase, get the bag to where I want it to go. When it better hit that boundary condition before I run out of arm range of motion. And while I'm throwing this bag that is heavy, I have to think about the coupled inertia between the robot and the bag such that I actually achieve the 180 and get my feet facing the other direction at the end. And so all of these trade-offs happen within MPC and allows us to specify what's a pretty complex behavior without going through all the details of how to do it. So once you have the ability to tell the robot what to do at this kind of a level, we think we've got something that's pretty exciting. So now we can start to tell the robot to do other types of manipulation tasks through the same type of framework. And that's largely what we've been working on recently. So here's just a few examples of Atlas doing other types of manipulation stuff in the lab, grabbing various types of objects. We've kind of just been running around the building. We go rob the gym of its kettlebells and barbells and things like that, and grabbing tools out of the technician area, and seeing how far we can get just telling the robot to move things around. Some of this stuff is pretty heavy. So this is a wheel from a car, pretty heavy thing to just pick up and run around. Here's a full exhaust assembly from a car. So you can kind of reach out, grab it. And then the robot's thinking about the whole inertia of the thing as it's turning it around. It's thinking about the collision between that object and the fixtures that it knows about the environment. Here's some There's some other manipulation stuff where we're grabbing a heavy strut, doing a multi-step grasping here. And again, this is not just MPC by itself. There's some pretty sophisticated other components here that are being deployed that have to do with visual identification and tracking of very complex objects, such that we can specify sparse manipulation goals, like where to grasp the thing. But then once we have it in the hands, just being able to tell it where we want it to put the strut and not having to worry about all those coordination details and getting the robot to do things like this is pretty powerful. And you can just keep doing this. And the more we do this, the more examples, positive and negative, that we generate of the robot doing really complex bimanual manipulation tasks. And this gets back to this idea of being able to use MPC as an interesting way to easily generate new types of embodied data. So we're excited about continuing to push in this direction and get the robot to be more and more capable over time. But MPC is not a panacea, right? There's a bunch of stuff here that works really well. We think it provides a very useful interface for controlling complex behaviors in robots like this with some ability to generalize. When you make changes to it, it has this nice property that those changes carry over to all the other places where MPC is used, right? So when we added collision geometries into MPC in order to do this crazy tuck spin thing, that immediately benefited our ability to do step recovery, right? So now the legs all of a sudden don't collide when we want to do a cross step, for example. The downside, of course, is it depends on good models and state estimation, right? So MPC is about as useful as the predictions it makes. And so if it's making poor predictions about the environment or just doesn't know about relevant dynamic things happening in the environment, things can go badly. And this is really only solving a slice of the problem. In order to really make an MPC powered system do amazing things, you still need lots of things living upstream, planners, decision-making, perception, and so on. But that leads to another question. In what ways can we use RL to improve the performance of MPC, make MPC powered systems do more? So I'd like to tell you about quickly tell you about another project where we've looked at trying to use RL policies in order to improve the performance of MPC applied to production spot locomotion. So before I start talking about Spot, I wanted to just provide a baseline so we're all oriented here. Spot is an amazing locomotion machine. And I can talk this way about it because I am not at all responsible for creating the controls. So this is really, really impressive. This is an example of us taking a field trip out into the woods. This is early days and we're starting to explore ways we might use RL for spot locomotion. And we were trying to drive it around on gnarly rocks and things like that and try to get it to fall. And we just left really discouraged that there wasn't that much of a problem left to solve. And so, the robot's doing things all the time. Here's some fun stats. So the robots have cumulatively walked over 250,000 kilometers worldwide in all kinds of environments, indoors, outdoors, industrial, and so on. And they're running 24/7 day and night. So they currently accumulate the circumference of the Earth every 3 months in customer's hands. So it's, basically thousands of these robots doing stuff all the time. It's cool. So that's our starting point. But nevertheless, we still do find corner cases where the robot does fall. And so here's an example. This is real data from a customer site. And they're sort of weird things, right? So here it's entering into a soapy, slippery floor where there's an adjacent hurdle. It's like that combination of things causes the robot to fall pretty reliably. And we can actually reproduce this in the building. And so the way that this works is this kind of thing happens. We get automated logs that load up into engineer dashboards. Engineers can look at this stuff and try to root cause it and then figure out how they're going to fix it, package it in the next release, rinse and repeat. In this case, the module that was thought to be responsible for this failure was this thing here. So without going into too much details of Spot's control system, basically it's running MPC. And there's a whole bank of MPC controllers that are all running simultaneously. And there's some selection mechanism that at any point in time is selecting from among this MPC solutions and then running it on the robot. This selection mechanism is something that's quite complex. It's been tuned over many years, and it's responsible for all of Spot's locomotion. So this is used all over the place, all types of environments, scenarios, and so on. So making changes here is a pretty complex thing, right? And so making a change here just to address this without degrading performance globally, not so clear. So the question was, could we use RL basically to solve two things? One, do better. So make the robot not fall in scenarios like this, and ideally not degrade performance globally, but also simplify this whole picture, right? So maybe we don't need to run N MPC controllers all together at the same time do selection. maybe I can just have one RL policy that outputs the appropriate parameters for a single MPC instance and, do better. And so that's what we did. So here's just a picture of a variety of simulation scenarios. So when we run training, we have a huge parameterized bank of possible locomotion environments that cover what we think are all of the interesting spot use cases. And then we started by behavior cloning the existing system and then running RL from there over this distribution of environments. And it turns out you can do better. So here's just some examples of the RL policy being evaluated in what I call the target scenarios, the places where we wanted the system to do better. And so these are simulations. You can see it does a lot better in very slippery environments. It does a lot better in areas where there's kind of weird rise-run combinations for staircases. And then also when friction is varied in these types of scenarios. And there are some examples where you can't even get the production controller onto this box, basically. And so RL is able to do quite a bit better here. And yeah, so you can do these kind of tests, but one question remains, how do you know when you can ship this thing, right? And that's a really hard question. And so our approach to doing that is extensive robustness testing. So not only just running exhaustive batch simulations in order to do statistical analysis on performance of the system, but also doing it in hardware. So I can create, specific test scenarios that run autonomous missions for hours and hours and hours and hours and hours on the things that I care about to make sure that it actually does better at something. And then we can look at regressions in performance using a robustness fleet that runs 24/7 all the time in our building. And so there are spot robots that walk just around on flat ground, that climb over hurdles, that climb over boxes, that walk on wood stairs, that walk on graded stairs, open face stairs, walk inside, outside, in fake rain environments, in stones and dirt, opening doors, closing doors, all kinds of stuff all the time. And so when you have a change, you can deploy it to this fleet and quickly collect thousands of hours of experience and statistics about mean time between failure to know whether you've made a change that is better or worse or not different. And this is really important. Okay, cool. So I'll stop with a few just concluding thoughts. I think MPC powered robots can do a lot, and I think we haven't found the limit of what they can do. And at the very least, I think they're a very compelling source of data, embodied robot data. When you're using learning or not, you're just making changes to a complex system that's used in a wide variety of environments by real people. Doing robustness testing is essential. It gives you confidence that the thing you're about to ship is actually better. And when it's not, and you eventually find those failure cases, being able to quickly identify them and root cause them and ship fixes is extremely important because the patience of customers through failures is not super high. Challenges to scale. So we, as Stefan said, Boston Dynamics spent many, many years building locomotion technology. And so the first time we shipped it, it was already pretty good, right? It was not as good as it is today, but quite good. I think for open world sort of industrial manipulation stuff that we're excited about for our robots, the early versions of that aren't going to be super reliable. And so how do you actually start the flywheel here? How do you deploy skills that may not be super reliable in the world in a way that can generate data that will eventually lead to improvement? And so there may be some considerations here that are a mix of doing a really good job building the first versions of things. Maybe there's some strategies for managing expectations with future customers, building in good mechanisms for graceful failure recovery, and so on. Safety and predictability is huge, right? So actual safety, saying something about the safety of your robots is really important to a lot of customers, but also the perceived safety of robots is really important. So we saw this with Spot where its ability to go up and down stairs quickly is at least as reliable as its ability to go up and down stairs quasi-statically, but customers strongly prefer the quasi-static one because it looks safer. And sometimes you just have to succumb to that. And so that's sort of interesting. Customer data access is not always easy, right? So when these robots are operating inside of commercial facilities that may have proprietary equipment, products, things like that, It's not always so easy to get unfiltered data back in order to improve the system. Ability to reproduce in simulation is really important. So yeah, it's great when we can look at a specific case and build an actual setup in our building in order to reproduce it and then use that for testing improvements. But that's not really scalable. When there's 10,000 or more of these robots in the world experience all manner of corner cases, the ability to quickly take those corner cases and reproduce them in simulation feels pretty valuable. And then along those same lines, maybe if there's opportunities for us to directly learn from failures in the data of deployed robots and ship improvements over time, things like offline reinforcement learning, for example, I think that would be really exciting and as an open opportunity. Yeah, and that's it. And we are hiring. So if you're interested in reinforcement learning, machine learning, applied to crazy dynamic robots, you can check out these specific openings, or if you're just generally interested, Scott K at Boston Dynamics. And that's it. Happy to take questions.
Maybe you have time for 2 quick questions.
Yeah, thanks for the great talk. Really enjoyed it. So you mentioned that you need to specify reference trajectories, right, for MPC. And it seems like, both Atlas and Spot have a lot of joint angles and, a lot of sort of moving components. So are the reference trajectories specified in the workspace or in the C space, like in the angle space? And how do you specify such complicated reference trajectories?
Yep. So depending on which video you're looking at, the answer is different. So for things like backflips, we give a full joint space trajectory that usually comes out of an offline optimization. It looks kind of like MPC, but it's usually bigger with more details and stuff. Or it could be things like animation, motion capture. Motion capture is easy when you have a humanoid and you have humans, that's good. And for manipulation, usually we'll have a pretty trivial joint space trajectory. So something like stand at some nominal posture, and we're just directing it where to put its feet and hands in order to do grasping and lifting and placing. And so what you'll, I think, see if you look closely at the videos of manipulation is the robot motion tends to look a little bit less polished because MPC is doing a bit more innovation, but it's way easier for us to generate those inputs and even do it online.
Thank you. While it's set up, we can take more questions. She's still sitting.
Thanks for the great talk, Scott. I wonder when debugging MPC, if something didn't happen as expected, how do you attribute the failure to model error, solver, state estimation, and cost function? Could you give us some secret formula? And which part of this is a bottleneck in cover?
No.
Yeah.
The real answer is really good analysis tools. So you want to log basically everything and have good ways to visualize in different ways the data that you do log. And I think over time, if you mature the tools you have for debugging, doing FA, you're going to accelerate everyone's work. Yeah. So there's no like catch-all answer for that, but good tools are really important.
Thanks.
Maybe we can take the last question for you. It's really quick.
So kind of similar on the just dynamic situation. How does the MPC react to something like changing dynamics of a grasp object? Like kind of a niche scenario, but what if it was to pick up a bag of sand that is leaking and actively changing its mass over time?
Yeah.
Can it take that into account in its planning?
Yeah, so the way that we would set that up is you'd have to have a separate estimator that's continuously estimating the properties of the object in addition to its state. That's, I think, the way to implement it. In the things that we showed here, it's not doing that. So if magically half the mass disappeared from the object, then it would be something undefined.
Great. Thank you.
Yep.